Let e sub 1 and vector e sub 2 be the elementary vectors in R2. And let y sub 1 and y sub 2 be two vectors in R2. Now, we want to let t from R2 onto R2 be a linear transformation that maps the elementary vector e sub 1 to vector y sub 1, and also maps the elementary vector e sub 2 to vector y sub 2. And our job is to find the images of vector 5, negative 3, and the arbitrary vector x defined as x sub 1, x sub 2. Okay, so let's get started here by simply thinking about what exactly we are given. Well, we have the transformation t from R2 to R2 is a linear transformation. So this linear transformation is closed under vector addition and scalar multiplication. It's also given to us here that this linear transformation t takes the elementary vector e sub 1 and maps it by definition to the image of the elementary vector e sub 1 under the action of t, which is defined here as vector y sub 1. Now, this linear transformation also takes the elementary vector e sub 2 and maps it to the image of vector e sub 2 under the action of t, which is defined here as vector y sub 2. And now we're given specific values for these two y vectors. Y sub 1 is defined as the vector 4, 6, and the vector y sub 2 is defined as, or defined by the components, negative 1, 8. So this is what we're given, and this is going to be important to keep in mind as we proceed. Now, we want to find two things. So the first thing that we want is the image of this vector 5, negative 3. So the image of this vector, this is equivalent to saying we want to find the image of the vector 5, negative 3 under the action of t. So we'll start with this part 1. How are we going to do this? Well, the first thing that we need to do is decompose this vector 5, negative 3. So we want to decompose the vector 5, negative 3 into a linear combination of the elementary vectors. So we know that vector 5, negative 3 is equivalent to 5 multiplied by the elementary vector e sub 1 plus negative 3 multiplied by the elementary vector e sub 2. So these two forms are equivalent, but this second form, this linear combination of the elementary vectors, is going to allow us to apply the properties of a linear transformation. So here we go. We want to find the image of this vector 5, negative 3 under the action of t. So we just decompose this. So this is the image of this linear combination, 5 times the elementary vector e sub 1 plus negative 3 times the elementary vector e sub 2. Now, since t is a linear transformation, we know by definition that it preserves the operation of vector addition. So in other words, the image of the sum of vector u plus vector v is equal to the sum of the images. Need a little bit more room. And we also know by definition of a linear transformation that the transformation preserves the operation of scalar multiplication. So we have the image of the scalar multiple c times vector u under the action of t is equal to the scalar multiple of the image of vector u. And again, this is of course such that vector u and vector v are in the domain of our transformation, and c is any scalar. So just by knowing that this transformation is a linear transformation, we can apply these properties. So let's do that here. We can further decompose this image to the sum of the scalar multiples of the individual vectors. So we have 5 multiplied by the image of the elementary vector e sub 1 plus negative 3 multiplied by the image of the elementary vector e sub 2. And now this is particularly helpful because we know what these images are. They're given to us at the start. Woohoo! So we can plug those in. We can say that this is equivalent to 5 times vector y sub 1 plus negative 3 times the vector y sub 2. Or in other words, this is 5 multiplied by that vector 4, 6 plus negative 3 multiplied by that vector with components negative 1, 8. And so this is equal to 5 times 4 is 20, 5 times 6 is 30, plus negative 3 times negative 1 is positive 3. Negative 3 times 8 is negative 24. And by vector arithmetic or addition, we are left with the vector 23, 6. And so therefore, we have our beautiful final answer. We have the image of the vector 5, negative 3 under the action of t is equal to the vector with components 23, 6. And so this is our beautiful final answer to the first part of this question. So in part 2, we are asked to find the image of the vector x sub 1, x sub 2. So we'll keep in mind here that, in other words, we're being asked to find the image of this arbitrary vector x sub 1, x sub 2 under the action of t. So in order to find this image, we again need to start by decomposing this vector into a linear combination of the elementary vectors. So we want to decompose this arbitrary vector in R2, this vector x sub 1, x sub 2. So here we go. We know that this is equivalent to the scalar x sub 1 times the elementary vector e sub 1 plus the scalar x sub 2 multiplied by the elementary vector e sub 2. So now that we have this decomposition, we're ready to find the image. So here we go. We have the image of the vector x sub 1, x sub 2 under the action of t is equivalent to the image of this linear combination x sub 1 times the elementary vector e sub 1 plus x sub 2 times the elementary vector e sub 2. And we'll make a little love note here to ourselves that since t is a linear transformation, we know that this is closed under vector addition and scalar multiplication. So we can further decompose this image and say that this is equal to the sum of the scalar multiples of these images. So we have x sub 1, our scalar multiple x sub 1, multiplied by the image of the elementary vector e sub 1 under the action of t, plus our scalar x sub 2 multiplied by the image of the elementary vector e sub 2 under the action of t. And we know by what is given in this question that this is equivalent to x sub 1 multiplied by vector y sub 1 plus x sub 2 multiplied by vector y sub 2. So plugging in those vectors, we now have x sub 1 multiplied by the vector y sub 1, which is defined by the components 4, 6, plus x sub 2 multiplied by vector y sub 2, which is defined by the components negative 1, 8. And we can further simplify, so we have the first column vector is 4 times x sub 1, 6x sub 1, plus our second column vector becomes minus x sub 2, 8x sub 2. And so we can make our final conclusion and say that therefore the image of this vector x sub 1, x sub 2 under the action of t is equal to the vector 4x sub 1 minus x sub 2, 6x sub 1 plus 8x sub 2. And that is our beautiful final answer.